All right, so let's continue. In the previous lecture, we started looking at the example. All right, so we wanted to find the net electric field created by a charged ring. So what was given? Uh, okay, you're still chatting. Guys, keep your mics off, right? Because there is a feedback, audio feedback. All right. Okay. So what is given? Let me quickly remind you. So we have a uniformly charged ring. Radius is given. Total charge is given. We want to find the net electric field at the distance z from the center of the ring. Right. So what was the beginning? So we said let's take infinitesimally small section of that ring of length dl with the charge dq, right? And since it's in infinitesimally small, so we can treat it as a point charge. So we decided and we treated it as a point charge. And then the next step, of course, we need to write all these quantities in terms of what is given and a variable of integration. So first, r squared, distance from the charge to the point in question, it's r capital plus r squared plus z squared, all right? And then we wrote dq in terms of what is given and the variable of integration. So it's a linear charge distribution, so we use linear charge density times dl. We discussed it in the previous class, right? And we found linear charge density as a q divided by the total length of the ring circumference, right? And so that's what we got. So then, of course, we plugged all this and that into our dE, and we ended up with this expression. Basically, we need to understand that this is magnitude of okay, I'm trying to find whose mic is still on. Okay, all right, so it's a magnitude of a vector. So this is our vector and this is its magnitude. So at this point, if you just grab this expression and start integrating, hoping to get the net electric field over there, it's just wrong because we're dealing with a vector quantity. Vector quantity must be treated properly. What does it mean, treating it properly? You need to find each component of the vector and integrate components. That's the correct approach of dealing with the vector quantities. So basically, after this point, we were supposed to find x component of this dE. Basically, over here, there will be x component, and integrate it over the whole ring. Then do the same with the y. So find y component of this electric field and integrate it over the whole ring. But since if you look from this point, we have a nice nice level of symmetry. Again, if you look at from this point on the ring, you will see that there is lots of symmetry. So let's try to use that symmetry. Maybe we can skip this integration to find the y component of the electric field, right? So that's what I wrote. Let's use symmetry to skip integration in the y direction. Okay, so what do I mean by using this symmetry? So this is our section dl. But of course, for this section dl, we can find symmetrically positioned section on this side of the ring. I can extend this, and over here, I can find symmetrically positioned section with the same length dl and which will have the same amount of charge dq. So basically, diametrically opposite section, right? And of course, this section is going to create its own contribution to the net electric field at this point. Let me draw it. Okay, so it will be, let me draw this line first. And of course, this electric field can be represented by this vector. Yeah, good enough. And since dq here and dq there are the same, and this distance and that distances are the same, so length, the magnitude of this vector and magnitude of that vectors are the same. Of course, vectors are different because their directions are different, but magnitudes are the same. So now let's look at the components of these two vectors, x and y components. Okay, let me start with the blue one. So this will be the x component of this blue vector. This will be y component of this blue vector. And now let's do the same with the red one. Of course, the red one will have, this is the x component, and this will be the y component of this red vector. And now let's look at the y components. This y component and that one. They're the same in length, but opposite in directions. So they cancel each other. And so now we can say, so for any section DL on this, over here, for example, or over there, it doesn't matter. I can find diametrically opposite section over here. And every time their y components will be canceled. So it means what? When you start integrating, at the end, every time you will end up with 0 y component of the electric field. So just by looking at the picture, analyzing the symmetry, you can tell immediately that this integral will give you 0. Of course, if you don't trust me, if you don't believe me, okay, your justification, your arguments, complete nonsense, okay, not a big deal. Find y component of this electric field, integrate it, and you will get that 0 mathematically. But we just want to save some time and use the symmetry. Exactly the same, okay, very similar arguments we applied when we integrated one problem in our recitation class. Right. Okay, so now I can write as a result. All right, so E sub y equals to 0. So by just using the symmetry of the problem, we can tell immediately that the y component of the electric field at this point will be 0. But x components, of course, you see, they don't cancel each other. They actually add each other, right? So it means that we need to carefully integrate it. So we need to find first x component of this vector. So we just need, okay, maybe I will write, so let me write this down. So over here it will be dE sub x, right? So we need to find that and integrate over the whole ring. Right. Okay, so now let me write that down. Probably I will start with dE sub x. Of course, it will be dE. And in order to find this component, all right, so this one, I need to introduce, most likely, I will introduce this angle, and let me call it theta. We need that. And now, okay, maybe first I will write, so it's a times cosine theta. So since we need to find a side adjacent to the angle, so we use cosine angle. All right, so now we need to find this angle theta. And in order to find that angle theta, or maybe write in terms of those, what is given and in terms of variable of integration. It depends on the problem. But anyway, look, this angle and this angle are the same because they are vertical, right? So, and finding that theta from this right triangle is a piece of cake, right? So we can now find cosine theta using this triangle, this point, and that point. Okay, so let me open my explanation box over here. And from this triangle, I can write so that cosine theta equals, of course, adjacent side, which is z, divided by hypotenuse, which is r small. Right? You see this. This is 90 degrees, so this triangle is the right triangle. Right, so it will be z divided by r. Or I can write it, of course, since r small we found over here, it's a square root of r squared plus z squared. We can write it in this way. So square root of r squared plus z squared. Okay, so let me close it. And that's what we can use instead of that cosine theta. And dE, of course, we take it from here. So now let me combine this dE with that cosine theta. And underneath, I will write, right, maybe I will rewrite dEx. And instead of dE, it's this. KQ dL, I'm just rewriting it, nothing else, 2 pi r. Then r squared plus z squared. Okay, so just I rewrote dE, and now cosine. This cosine will be here times z and square root of r squared plus z squared. Okay, so now basically we can combine this bracket with this square root. They will give us power of 3 over 2. So now we can start integrating. So that is the x component. We have a single variable of integration, right? So now we are all set to integrate it, right? So now I can write, so e sub x will be integral of dEx. And now I will just rewrite that, of course, combining. So it will be integral k q z dl. This z, I'll move it over there. Divided by 2 pi r. And as I said, this bracket with that square root can be combined, and they give us the power of 3 over 2. So it will be r squared plus z squared to the power of 3 over 2. So that's the integral over the whole ring integration. Right now, I haven't put any limits. And let me ask you, does it look scary, this integral? Usually,
a little bit, yeah.
Students' response kind of, oh my God, what the hell is this, right? So what should I do with this? It looks really, really scary, right? But calm down. Let's look at this, right? What k? K is the constant. Any constant factor can be taken outside of the integration, right? Then q, given constant, I don't know, 5 coulombs, can be taken outside. Z, your boss told you, measure the or calculate the electric field, I don't know, 5 meters from the ring. Basically, Z is also given. So also Z can go outside. 2 constant. Pi is also constant, also outside. R is given constant, also outside. R and Z, again, constant, also can be taken outside. So basically, all this construction, scary construction, it's a constant. So it's a constant, and it can be taken outside of the sign of integration. So as a result, integral is actually trivial. Yeah, it looks scary, right? But if you start analyzing, it's the easiest possible integral. Okay, so now let me rewrite with these modifications or simplifications. KQZ over 2 pi r and r squared plus z squared to the power of 3, 2, and integral over dl. So now that's what we have. Of course, strictly speaking, what we have over here, this integral, it's still calculus 3, integration over a line, right? And some of you, okay, most of you didn't take this course. But we should be able to write the answer of the value of this integral easily. Everyone can write that down. Because effectively, what is that? You're just adding. Integration, it's a fancy word for adding small things. Integration is just adding, and we're adding DLs. So if you start adding these small DLs, DL plus DL plus DL plus, and you keep adding, moving around the circle. So if you add all DLs, what are you going to end up with at the end?
The circumference.
Of course, circumference. Just 2 pi r. Again, strictly speaking, it's a calculus 3, but we know the answer. And that's what we're going to do many times in this course. We're going to deal with quite complicated integrals, but we're going to use high school knowledges, right, in order to write down the answers. Okay, so we can write immediately that this is equal to 2 pi r. And as a result, we have 2 pi r here downstairs, and we have 2 pi r there in the numerator. Of course, this 2 pi r and that 2 pi r will be canceled. And we're getting the answer. That's it. So as a result, I will write probably underneath, E sub x will be equal k q z divided by that r squared plus z squared to the power of 3 over 2. Okay, I hope I haven't lost anything, right? So let me check my answer. Yeah, that's absolutely correct. So that's the x component. of the electric field, and the y component is 0.
So, question.
Yeah.
So you're saying that when you take the integral of dl, it ends up being 2 pi r?
Yeah.
Okay, and that will cancel out with the 2 pi r on the bottom?
Yeah.
Okay.
Usually I write this 2 pi r over here above, but I have a constant over there written, so that's why I wrote it below slightly. But you see it, right? It will be cancelled. Okay, so let me frame this also, second part of the solution. So that's the answer. Right. Okay, so this example, as I told you, and the example from our recitation class problem, probably the two most challenging problems from the calculus point of view. Right.
Does the x component take into account that it would be from both?
No, this is the net. This is net. So pretty much what integration does, right? So we over here, we found contribution to the net electric field from this small dq. But then next section, next small dl will create its own contribution. So we just need to add these two. Then the next one, again, there will be contribution. So we need to add that also. And then we keep moving around the circle, keep adding these dEs. And that is the net electric field. Okay, next net x component, right? So pretty much pointing that way.
So that is basically is the sum of all of the x components?
Yes, okay. Yes, exactly. But of course, if you add all y components, they all cancel each other brutally, right? Giving us 0. Right. Okay, so that's what we need to discuss in this example. And now I will switch to the PowerPoint presentation, and we will continue from here. Done with this example. Okay, let me. Okay, probably I need to cover it. So now,
Professor,
yeah.
I have a quick question. Can we expect to see something like this on the exam?
Okay, I mentioned, okay, I don't remember, did I mention it in the recitation class or on the lecture? No, I usually tend not to give the integration on the exam, this type of integration on the exam, right? At least about the electric field, because again, as I already mentioned several times, some of you quite comfortable with integration. Some of you did not, don't know much of an integration at this moment, right? So as a result, I usually don't give on the exam. Homeworks, yes. In the homework, you will have one problem about integration, but on the exam, no. Okay, so now that's the example which we just discussed, right? And now let's use these results. So now, using what we just derived, using these results, we can also find the electric field created by a charged disk. So there we had a charged ring. Now, what if you apply these results to find the net electric field created by a charged disk, like you see here, right? So you see, now we have two-dimensional charge distribution, right? And, okay, we're not going to do another integration. If you want to read, you can read the book. All right, it's done. We're going to just show the results, right? So, again, it's an electric field created by this uniformly charged disk with surface charge density eta. So now we have two-dimensional charge distribution. In the previous example, we had one-dimensional charge distribution, here two-dimensional charge distribution, and as a result, we introduced eta instead of lambda, right? Okay, so, and again, the electric field at the distance z from the center of the disk. Okay, so, and that's the electric field, again, pure in the x direction. That's basically x component. Okay, and now again, we're not going to derive it. Now let's look at the limit of this expression. What if, for example, this disk is the size of the disk is gigantic relative to this distance z. So basically, what if r is much, much larger than z? Basically, with this limit, we will look at an infinitely large charged surface. So radius is gigantic, and the distance from the disk to the point where you want to see electric field is much, much smaller. So if you look at this limit, and at this point probably you should be comfortable dealing with limits. So if you use this limit here downstairs, z is much smaller, so we can neglect it. Only r will leave, r squared. Then you take a square root, it will be r. As a result, you will have a ratio of z over r. And again, since z is much smaller than r, so all this term, this second term, gives us 0 in this limit. As a result, you will have only eta divided by 2 epsilon naught times that 1. So as a result, we're getting the electric field created by an infinitely large charged surface. And this formula you already used in your recitation classes when you try to slow down the motion of a proton in the presence of a negatively charged surface. Right, and I told you that we're going to derive that formula today. So here's that's how we can derive this formula. Right, and so what's the major feature of this expression? The major feature, it's a constant. Eta, it's a given constant, the surface charge density. And epsilon naught, of course, a universal constant. So it means that electric field created by that surface is uniform. So now we presented the first electrical system which can give us a uniform electric field. And from now on, most of the time, we're going to use uniform electric fields. Right? So it's a first system. Right? And again, major feature that it gives us a uniform electric field. So the same electric field strength at any point and the same directions. Okay, so now if you draw electric field lines, you remember we use them to visualize electric field. It will be something like this. Let's assume that surface is positively charged. You see, density of lines exactly the same everywhere. It means that electric field strength is the same. And plus you see directions. They up. Okay, above the surface up, of course, below the surface down, because you remember all the time electric field lines, they start on positive charges. Surface is positively charged, so they all start on that surface. So first system which can give us a uniform electric field. So as I said, okay, so the field doesn't depend on how far you are from the surface. Right, so electric field strength will be exactly the same. Okay, so now, after introducing this, now we can increase complexity, right, of the system in order to introduce a new electrical system, which we're going to use pretty much throughout the whole semester. Right. Okay, so now we know if you have an isolated, infinitely large charged surface, for example, positively charged. Again, it doesn't look like an infinitely large, but just to save space, right, I drew it this way. And of course, I can draw electric field lines, right? Again, they start on positive charges. Then, if it's an isolated surface. Now, what if we have an isolated negatively charged surface? It will be this picture, right? And again, you see now electric field lines and on the negative charges and on the plate. And again, the electric field strength is exactly the same. Right, eta divided by 2 epsilon naught. Now, of course, next logical step, what if we take these isolated surfaces and bring them close to each other? Of course, no touching, just close. And we will get something like this, right? So positively charged surface, negatively charged surface. And now, of course, we will have superposition of 2 electric fields, this red field and blue field, right? So like a Democratic contribution and Republican contribution, right? Superposition of 2 fields, right? Okay, so let's start with this red contribution. Let's take this first, this and that. So this line is over here, and this electric field line here, right? And of course, you see it goes through negative plate. Of course, some students gets confused. How come that this electric field line goes through this surface? Why not? These surfaces creates their own electric field independently of each other. For example, like here I have a table, right? So gravitational field, it goes easily through this table, right? So it's below and it's above, right? The same. So electric field goes through this plate, no troubles, right? And of course I can draw all the rest of these red lines. So this is just a red contribution from the positively charged surface. Now let's do the same and let's draw blue contributions. So it's this line over here, and now of course this line will go through this positively charged surface. And now let me draw the rest. And again, you remember, electric field strength doesn't depend on the distance from the surface. It's a uniform field every time eta divided by 2 epsilon naught. So it means that electric field strength over here, the same in absolute value, but opposite in the directions. So here, there will be complete cancellation. So these two fields cancel each other, these, right? So on that side, outside of this construction, electric field, net electric field will be 0. Exactly the same story on this side. Those two, blue and reds, cancel each other. But inside, between the plates, of course, they add each other up, right? So here, field will be doubled. So as a result, outside, this minus this, you will get 0. But of course, inside, you will just add these two contributions, and you will end up with the electric field inside of the structure. And of course, we call this structure as a parallel plate capacitor. So electric field outside of a parallel plate capacitor is 0. Electric field inside of a, okay, very often I just abbreviate like a PP capacitor, parallel plate capacitor. Electric field inside is doubled, and it's eta over epsilon naught. We're going to use this formula and this system pretty much throughout the whole course. All right, so every time our electrical systems are going to be either point charge or parallel plate capacitor. All the time, because they are the simplest possible systems. Right? Okay, so electric field created by a surface. Here we have factor of 2 in the denominator. Here we don't have a factor of 2 in the case of a capacitor. Okay, so now we introduce a capacitor, and I guess now at this point we can leave that behind, and of course it's from time to time again we will be using capacitors. So the next, at some point I used to look at this example, and then I stopped looking at the example in the lecture, because we discussed just yesterday in our recitation classes examples very similar. Basically, it's a physics 1 problem, motion over point charge in the presence of the electric field. In our recitation class, we looked at the motion of a proton in the presence of the electric field created by a surface, charged surface. Here, in the presence of the electric field created by a capacitor. That's the only difference. Right. So pretty much solution is very, very similar. Right. So you can look it by yourself, right? And of course there will be a problem in your homework very similar to that. Right. Okay, so I'm not going to discuss this example. At some point I stopped doing it. Okay, so now it's time to start moving towards the new fundamental law, Gauss's law. All right, it will be one of the equations in the set of Maxwell's equations. Actually, the first one. All right. And what's the beauty of having Gauss's law? Gauss's law eventually will allow us to find an electric field created by any system. And when we introduce Gauss's law, we will have basically 2 options which can be used to find electric fields. You can either use Coulomb's law with a probe charge, like what we've been doing up to this point, finding electric fields, right? That's one option. The second option, we will be able to use Gauss's law to find electric field. So it's good to have options, right? So if you don't like this option, you can use the second one. If you don't like the second one, use the first one. Nice to have alternatives, right? Okay, so we will introduce Gauss's law, but right now we're not ready because we need to introduce a few things prior to that, right? But let me first explain what's the idea behind Gauss's law in simple words. Okay, I usually compare it like with Yankee swap. I'm sure that all of you played Yankee swap at some point, since even I played it a couple of times, and I'm usually the last one who does anything new. Right, so how does it work? So there's a table, right, filled full of boxes, right, and inside of each box there is some present. And of course, your goal is to pick the box with the best present inside, right? And then what happens, sort of procedure? You go to the table, you pick the box, right, and you start exploring the surface of the box because you're not allowed to open the box to see what is inside, right? So what is available? Only the surface of the box. Of course, you can I know, weight the box, you can shake it, you can I know, smell it, kiss it, right? You can do anything you want, exploring the surface. And the goal of your explorations is to guess what is inside. Of course, very often it can be disappointing, some useless piece of something, right? All right. But again, the procedure, you explore the surface in order to predict what is inside. Gauss's law does exactly the same, but in the fancy terms. So in the Gauss's law, there will be some surface, closed surface, some box basically. We will explore the electric field in order to predict the amount of charge inside of that box. Basically a fancy Yankee swap, right? God created for us, right? So that's what we're going to see in the Gauss's law. But for now, we're not ready to introduce it completely, right? So for now, okay, so here's another example. Right? I took it from the book, I almost forgot. So for example, let's say we have this box. And inside of this box, there might be charges. And we don't know what is inside. But let's say we took a probe charge and we explored the surface. And let's say we found that there is electric field lines pointing that way. What can you say about the charge inside of this box? We should be able to tell immediately that net charge inside of the box is positive because electric field lines are getting out. Right? You remember, electric field lines, they start on positive charges. You see, even without knowing Gauss's law, without knowing anything, we can tell immediately, we can predict, we can get some information about the net charge inside of this box. So you see, there must be a relationship between, or relations between electric field on the surface and the amount of charge inside. Or it's second example, right, again from the book, right? So similar situation, but now electric field lines are getting into the box. So again, we should be able to tell immediately the net charge inside of this box must be negative, right? So it's just an example that there must be a relation between the electric field lines on the surface and the amount of charge inside. And now let me state sort of the Gauss's law in the words, right? So it looks like if we count number of electric field lines, 100,000, crossing the box, crossing a surface, it is reconnected to the total amount of charge inside of the box. It's my actually Boston Marathon mug, right? From my days, right, of running, right? So I'm using it to demonstrate Gauss's law, right? Right, so again, so Gauss's law relates number of electric field lines crossing the surface, crossing the box, with the total amount of charge inside of the box. Which part of this statement which part of this statement is the most confusing for you? At least that would be for me the most confusing. What does it mean? Number of electric field lines. Of course, you can draw thousands, you can draw a few, right? So right now it's not a very well defined term. How can we count number of electric field lines crossing a surface? So now that's why right now we're not ready to introduce this Gauss's law. We will most likely introduce it next lecture. Now we're just moving towards that. Now we need to learn how to count those electric field lines. Basically, we just need to introduce a new tool, completely new quantity, which is called the flux, electric flux, a very important quantity. When we move to the magnetism in a couple of months, we will introduce magnetic flux, but here we need to introduce electric flux. And physical meaning of this quantity is basically number of electric field lines crossing a certain surface. Of course, for me, whenever I hear the word flux, first associations in my head, it's with the flux capacitor in Doc Brown time machine, right, from Back to the Future, right? But of course, they have nothing in common, right? But the movie is good, and that's my first, those are my first associations, right? So anyway, so now we need to introduce the idea of the electric flux. Again, it's a number of electric field lines crossing a surface, right? Okay, so that's what we need to introduce today, and then on Thursday, Gauss's law. So first, which quantity must be involved in a definition of the flux? Here I just wrote some words, right? So which quantities must be involved? Let's imagine this situation. Let's say here there is a fan blowing air, all right, through this surface, through this loop, right? It's my surface. And let's say I want to know the amount of air crossing this surface per unit time. I don't know, maybe 3 liters, maybe 5 liters, right, per unit time, amount of air, all right, or number of molecules. So of course, first quantity on which the amount of air should depend on how fast those molecules travel. Of course, if they don't travel, if their velocity is 0, of course, none of the molecules will be able to cross this surface. Or if they travel very fast, of course, large number of molecules and large amount of air will be able to cross this surface per unit time. All right? So if we connect with our electricity, with our electric fields, it means that that flux must depend on the electric field strength. So electric field must be involved in this idea of the electric flux. First quantity, electric flux. The second is obvious. The larger the surface, the larger amount of air will be able to cross this surface, and in our case, the larger flux is going to be. So the larger the surface, the larger flux. So the second quantity must be the area. So electric field, then area, and the last quantity which must be involved. Of course, if, for example, I position the ring like this, perpendicular to the direction of motion of molecules, right, of course, we're going to get the largest amount of air crossing this loop. But if I start tilting it, of course, less molecules will be able to cross it, right? And if I keep tilting, right, the amount of air will become less and less and less. And in the case when the ring is horizontal, of course, none of the molecules will be able to cross this surface, right? And as a result, air wouldn't be able to cross this surface, this ring. Okay, in our case also, there must be, in the case of the electric flux, there must be some angle involved in this definition, so that we can describe this orientation of the ring relative to the electric field. So 3 quantities must be involved: electric field, area, and some angle. Which angle, of course, it's up to us, but I will show you which angle was chosen, right? Okay, so now these 3 quantities, and before I can actually write down the formula for the electric flux, let's introduce this very kind of strange artificial vector, area vector. And the goal of this, if introducing this vector, just to simplify notation of the electric flux, right? And again, this vector will be used, we will use a lot, again, when we move to the magnetic world, again, we will use this area vector. So sooner or later, you will remember it. So what if you have, for example, what's the idea of this vector? Let's assume that we have this surface. Okay, this surface, the book, right? So by definition, it's basically mathematicians introduced this strange, artificial, weird vector to simplify notations of the electric flux. So by definition, don't try to find any logic, right, or any ideas. There is nothing. The idea was just to simplify the formula. Okay, so by definition, this area vector perpendicular to the surface. First, period. All the time, by definition, area vector perpendicular to the surface. Second, magnitude of this area vector equals to the area of the surface. Two parts. It's perpendicular, and the magnitude of this vector equals to the area of that surface. That's how area vector is defined. Here, there is one ambiguity, because if you have a surface like this, you can point area vector this way or that way, no restrictions for now. But maybe, like, I hope, or maybe next class, at some point, when we move to the closed surfaces, I will remove that freedom from you. But for now, when you have a surface like this, area vector can point this way or that way. All right. Okay, so that's how area vector is introduced by definition. Oh, this example, you have a rectangular surface and area vector perpendicular, and magnitude of this vector equals to the area of the surface. Or again, direction can be picked downward. There are no any restrictions. All right. So if you have surface like this, you can point it up or down. For now, you have freedom. Or circular surface, right? Any surface. For any surface, you can introduce area vector perpendicular, right? But of course, in this case, it can also point this way. Right? Okay. So now, after introducing this area vector, we can finally write down the first expression for the flux, but for the simplest possible situation. So simplest. What if we have uniform electric field? Because you remember, three quantities must be involved: electric field, area, and the angle. So what if we have uniform electric field and a flat surface? The simplest possible situation. A uniform electric field, you see density of lines are the same, at least I try to draw it this way. And the surface, let's say this circle. All right. And so now, you remember we introduced area vector to simplify notation, so let's draw electric field. Area vector. You can point the area vector that way or this way. It doesn't matter. Let me point in the direction of the electric field, that way. All right. And angle which we're going to use, it's this angle between the area vector and the electric field. This angle. All right. And now, for this situation, mathematicians introduced a new tool, electric flux. And we introduce it in this way, as a dot product or scalar product between these two vectors, electric field vector and the area vector. Dot product, scalar product. You remember from physics 1. Right. So, of course, if you write it explicitly, it will be magnitude of E, magnitude of A, times cosine of the correct angle between two vectors. How can we find correct angle between two vectors? Right. In order to find the correct angle between two vectors, you need to position ends, right, tails of both vectors at the same point. Let's say this is the end of the vector and this is the tails, right? So you need to position tails of both vectors at the same point. And this angle less than 180 degrees, or this angle, is the correct angle, right? I will keep reminding you about this sort of definition, how we can find the correct angle, right? And this is the correct angle because you can just slightly move this electric field vector forward, and their ends will be at the same point, right? So this is the correct angle. So that's how we can find number of electric field lines crossing this surface. That's the physical idea of the electric flux, a very important quantity. In a couple of months, we will introduce magnetic flux in a similar way, but now electric flux. Okay, so now, first example, I'm not going to poll it. You see, no polling, right? Because I just want to discuss it without asking you. So let's assume that we have uniform electric field. You see strength 100 newtons per coulomb. So this is the electric field lines. And here's the surface, 2 by 2. And the question is, what's the electric flux? So we have a surface. There is an electric field. Of course, the electric field lines cross this surface. Of course, there must be electric flux. So what's the value? Okay, so it's our case, uniform electric field, flat surface, so we can use the formula which we just introduced, EA times cosine of theta. E, obviously, 100, area 2 by 2, 4 square meters. The question is, what's the angle? What's the correct angle? Because at this point, at the very beginning, lots of students picked the wrong angle because they looked at this, so electric field points this way, it's perpendicular to the surface, so the angle must be 90 degrees. No. How we can find the correct angle? It's the angle between vector E, electric field, and the vector A, area vector. So first, let's draw those two vectors in order to find the correct angle and avoid that silly mistake. So area vector, I will pick that way. Again, you have a freedom to pick that way, but let's pick it in the direction of the electric field, right? So that's the area vector perpendicular to the surface. And then next to that, let me draw electric field. Basically, I position their ends at the same, tails at the same point, right? And now, what's the angle between these two vectors? 0 degrees, not 90 degrees. Yeah, these electric field lines perpendicular to the surface, but the way we introduce the expression for the flux, we use the angle between these two vectors. So be careful, don't make that silly mistake. In this case, the angle is 0 degrees, two parallel vectors. The angle between them is 0. And cosine of 0 is 1. As a result here, the flux, the value of the flux will be 100 times 4 square meters, so it will be 400 newtons times meters squared divided by coulombs. So that will be the answer. All right. Okay, at the very beginning, lots of students made this mistake with the angle, but after these explanations, they usually stop doing this. Next example, again, no polling, right? This situation, so I turn or rotated the surface by 90 degrees. So now it's sort of horizontal, right? And again, the same question, what's the value of the electric field lines? Or what's the value of the electric flux? Number of electric field lines crossing this surface. So let's look from the mathematical point of view, strictly from the definition. EA times cosine of angle. Again, electric field is here. Area the same, 2 by 2. Again, the question is, what's the angle? Again, draw the area vector. Area vector, let's say up. But the electric field is horizontal. And only now the angle is 90 degrees. So angle is 90 degrees, right? And of course, cosine of 90 degrees is 0. And the flux, electric flux in this case, is 0. The flux is 0, right? Okay, that's for if you look, again, from the point of view of formula, from mathematical point of view. But sort of conceptually, you can get that 0 without even using that formula, because you remember physical meaning of the electric flux. It's a number of electric field lines crossing a surface. In our case, electric field lines, they are parallel to the surface, so they physically cannot cross that surface, right? So immediately, conceptually, you should be able to tell, okay, it's a 0, right? I'm not going to find your angle, right? So I can tell it immediately that the flux will be 0. All right. Okay, so we're going to use it, of course. All right. Okay, this question I prepared for you, but we ran out of time, and we introduced enough in order to start discussing electric flux in our recitation class. All right, so we will practice pretty much the formula which I just introduced for the simplest case when we have the flat surface and uniform electric field. That's what we're going to discuss in our recitation class. We will look at 2-3 problems, because this idea is very, very useful, right? And again, in a couple of months, when we move to the magnetic world, we will introduce magnetic flux. And there, magnetic flux is even more important, because the whole production of electricity is based on the magnetic flux. So, and then in the future, of course, we will spend less time discussing magnetic flux, because all these ideas we can just move it and use in the world of magnetism, right? So it's a very, very important quantity, magnetic flux, or electric flux for now, electric flux, right? Okay, guys, so let's call it a day. So on Thursday, there are a few slides I need to finish about the electric flux, and then I will introduce Gauss's law, and we will spend some time playing with the Gauss's law, because it's one of the fundamental laws in physics, right? And again, it's one of the equations in a set of Maxwell's equations. Very, very important, right? Okay, guys, thank you. If you have questions, you can ask, right? Otherwise, I will see you on Thursday.